Physics 2, Lab 3, Circuits. So the goals of this lab is to verify Ohm's law by relating voltage, current, and resistance in a series circuit, and then use Kirchhoff's voltage law by showing that voltage drops around a loop sum to the battery voltage. We are also going to observe how a capacitor charges and discharges in an RC circuit using a light bulb. And then we are also going to measure charging and discharging times to approximate the time constant and comparing the theoretical predictions. Just to summarize the findings of this lab, in a series circuit, voltage drops across resistors added up the battery's total voltage, and then the current was uniform throughout the loop. In RC circuit, the bulb began shining bright, then dimmed steadily as the capacitor charged, and capacitors charge/discharge followed an exponential trend consistent with the RC model. Now, when we're going into key concepts, the first concept we're going to look at is Ohm's law, which basically describes the relationship between voltage, current, and resistance, stating that current is directly proportional to voltage and inversely proportional to resistance. In parallel circuits, we're also shown that the total resistance is given by this equation. 1 over R total equals 1 over R1 plus 1 over R2, etc. Then we're also going to look at Kirchhoff's voltage law, which basically states that the sum of all voltage changes around a closed loop is 0. And the capacitance in RC circuits is a capacitor stores charge. During the charging and discharging, the capacitor voltages change exponentially. Now we're going to the experimental assumptions of setup. We can assume that the system has the circuit components, which is the battery, light bulb, wires, capacitors, and resistors. Now the surroundings are the earth and the table surface. Now looking at the equipment, we can see that we're going to have two 1.5 volt batteries, 2 resistors, clip leads, indicator bulbs, ammeters, and capacitors. And we are going to be recording the initial I values from the ammeters. Now looking at the first circuit we're creating, which is a series circuit, this simple series circuit is created using 2 1.5 volt batteries, 2 resistors, and 2 ammeters. And first we calculated the expected current, which is given below. And then after we recorded the measured current, and we can conclude that when the connection is reversed, the ammeter reading became negative, consistent with the current direction. Now continuing with the series circuit, we also did the voltage across the battery and resistors, and the sum drops to 2.6 is close to the measured battery voltage within meter tolerance. And then we also looked at the resistance, which is consistent with the nominal values of 40 and 100. Now when looking total of the graph of the round trip potential, we can see that the graph shows that the battery's 3 volt is dropped across 47 and 100 resistors, confirming Kirchhoff's voltage law. Now, moving towards the circuit 2, which is the RC circuit, to set up the circuit, we connected the capacitor and the resistor light bulb in a series with a battery. We then closed the circuit, the light bulb will light up. As we close the circuit, the light bulb will light up as the capacitor charges due to the initial current. When the battery is disconnected, the light bulb will fade due to the capacitors discharging throughout the resistor. And our goal is to measure the charge and discharge times for different resistor values. Now to continue this RC circuit, we can see that we observed the light bulb faded over time as the capacitor charged and faded again during discharge, and charging and discharge both showed a decrease in brightness. And then as you can see, we can see the measured times of the charge and the discharge. And the results specifically show that the capacitor charges and discharges exponentially, with the bulb fading as the current decreases, which confirms the expected RC circuit behavior. Now moving on to the discussion, we can see a what if, which is the question is, what if you charge a capacitor with no resistor in the circuit? How quickly will our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Now ideally the capacitor would charge instantly, but this model in the ideal version assumes a limited current. But in reality, this would not be instant because of certain things like wire resistance, capacitor internal resistance, and then inductance. And the reason specifically for the difference is that in real life instances, there are certain resistances that limit the current, which causes the delay to charging the capacitor, versus in ideal circumstances, there would be no resistance, so there would be no delay, and the capacitor would charge instantly. Thank you.